Last class. Let's see. Okay, good. Yeah, so we talked about increasing the heat gain of essentially box-based solar cookers. So in this example, we had essentially all the light that comes straight through into the box, plus whatever you can reflect off from the side reflector here by adding an extra reflector, increasing the aperture. So when we talk about it, so the important thing to think, of course, it's a very simple system, but the idea to understand is that when we think about efficiency, the efficiency will always have to do with output that you generate divided by input going into the system, very generally speaking from thermodynamics. So it's very important we think, okay, if you have some concentrator or something to increase the output, you need to take that into account. So in a very simple case, if you have a solar panel by sitting by itself, or if you have a solar panel with a big lens on top of it, and if the lens is much bigger than the solar panel, you need to account for that area. So it's tricky, and it gets trickier once we start talking about spectrum splitting and things like that. So in this particular case, just be aware that the area here will be something like that, multiplied by the intensity of sunlight coming in, which we will learn about next week. It's called insolation. It will be in watts per meter squared, multiplied by area, you'll get the watts coming in, right? And coming out, of course, it depends on what you're doing. If you're creating electricity, it's just current times voltage will give you the power, watts. We'll talk about that later. If it is simply heat, then it depends on the specific heat of the material. We'll do some simple examples. Okay? So what I mean by that is that the input here is very different than the input here, right? So just be aware of it. So when we talk about efficiency, we also have to account for losses, right? We talked briefly about it on Tuesday. If I add an extra surface here, I might have losses because of radiation, because I'm increasing surface area of my whole device. This is my entire system, right? So I might be increasing, I'm increasing the surface to increase the input power. I might also be increasing the losses. So we have to be very cognizant of all these things when we start doing the design, okay? So let's talk a little bit about the loss mechanisms, because these, of course, are quite important. There are first three things that can happen which allow a body to lose energy. One is, of course, conduction. So if you have a hot body in contact with another body, it can lose heat. And of course, losing heat means you're losing energy, right? So we're aware of that. We'll talk about thermodynamics next week, but just generally speaking. And the other option is radiation, which means that you're losing energy in the form of photons. We talked briefly about this on Tuesday. Radiation means that the energy is being lost as long wavelength photons. So the greenhouse effect, the short wavelength photons are absorbed. The longer wavelength photons, which refer to lower energy photons, are lost. They're radiated out. Okay. Again, we'll talk more about this in this class, but just have the general notion for now. Of course, convection means convection and conduction, by the way, in a sense are similar. The only difference is that convection means that you have a gas or a fluid, right? Conduction means it's a solid. That's the only main difference. In the case of convection, of course, because you have molecules that can move around, they can take the heat energy, the molecules in close contact to the hot surface will absorb the energy, and then it can move to the cold surface and release energy and come back and forth. So you get these convective cycles. This is what happens on Earth, obviously, right? So this is important to understand, because when we start designing new systems, we need to be able to understand and pick the configurations and materials to minimize losses. That is our goal. So just, again, very simple example here. We have to make sure that the absorber plate has to be insulated from the bottom of the cooker in this particular case, because you don't want to lose heat into the body of the cooker. You want to keep everything in here where the cooking actually happens. The radiant heat, you want to make sure that, like we talked about on Tuesday, the longer wavelength light is trapped by the container, the glass, foil, whatnot. So again, just to remind ourselves, what's happening here is that most of the light from the sun, let's say, passes through this transparent material. And generally speaking, the transparent material is opaque to infrared light, a very long wavelength light. So what that means is that when this black body absorbs those short wavelength light and heats up, it will start radiating. Any black body, anything that absorbs heat will also emit heat, like you and I. we have a body temperature. It is also emitting, right? We are emitting thermal photons all the time. We take a picture with a thermal camera, we'll see it looks very bright, right? And that's what I mean. There's photons coming out, but we are all black bodies. So that's exact same thing happens here. The only difference is that here we're trapping them. So the longer wavelength photons are not allowed to escape as best as possible. So we choose this material to be as opaque to longer wavelengths as possible, but as transparent to shorter wavelengths as possible. Okay, so that's interesting balance there. So you keep that trapped, and that gives you, increase in temperature of the system. So that's what I mean by this. So that choice of that transparent material can be whatever, plastic or glass. Of course, you also want to make sure it's well sealed, so you don't have heated air may leak through gaps, and that's convection, right? So if you have some gaps here, the hot air molecules can take the heat away, and that's not good either. So if you try to improve the design, those are the things you want to start thinking about. Again, this very simple example is useful to think, so you can actually kind of see the different aspects of it. It's not just the optics, the materials, the thermodynamics as well. Of course, the other thing is, at least in this specific example of cooking, you want to make sure, at least you would like to have the opportunity to cook while the sun is when the sky is cloudy. Right? This is an option, or a little bit into the evening if you can. And that's possible if you choose materials that have large thermal mass, which means that they can hold their heat really, really well. So that's what this refers to. So if you pick some materials which have very large thermal mass, it has high storage, heat storage capacity or heat capacity. And of course, insulation is also very important because you don't want to lose that heat. You will still be radiating, but you want to try to keep it in as best as possible. So thermal mass is the ability to retain heat, and higher thermal mass takes, of course, the trade-off. So what that means is that it can, the higher the thermal mass, you can retain the heat longer, but that also means that it will take longer to heat up to a certain temperature. We'll talk more about that. That's related to the specific heat capacity of the materials. From our point of view, we're not going to go into deep details about what that means, but we need enough to be able to calculate, temperatures and changes in systems and things like that. So that's the trade-off. So higher thermal mass means it takes longer to heat up. So again, something we need to be very aware of. Okay, so from the system level requirements, now we can start thinking about, okay, what are the different materials that we can use to satisfy these requirements? And again, very simple example, but useful exercise is to think about all this. So first of all, we start with structural materials. So these are all the same system. Typically, you want to use cheap stuff. So in this case, wood, cardboard, metals, bamboo, brick, stone, plastic, rattan, whatever. But the key thing is that in these things, you want it to be stable for wind and things like that, as we talked about on Tuesday, right? We saw some examples where if you have these panel cookers, they might be flying around, but you need some stability there, so that's important. Insulation, obviously. So insulation means this part needs to be insulated from the environment. You can use a variety of things, aluminum foil, down fibers, whatever. Right, cellulose, trisols. So just be aware of it. And of course, all these are also, the choice here is also driven by application and cost and where it's being used and things like that as well. So of course, we should be very aware of those things when we pick the materials. Transparent materials has to have a good greenhouse effect. So that's probably one thing to consider as well as cost. So glass is heavy, for instance, more expensive than plastic. So maybe that's not a best choice. High temperature plastics are not those two guys. Moisture resistance is important because many things that people cook emit water vapor. So you gotta be aware of that. Again, something may not think about until you actually try. So linear walls must protect the rest of the cooker from moisture. So if you have something that can cause bacteria or whatever, so it's something to be aware of. The temperature will help with bacteria, but something we should also think about. Okay, and some ancillary design considerations one also needs to think about, of course, are, which we haven't discussed so far. Size, is it appropriate for the amount of food someone, whatever needs to cook? Is it portable? We talked briefly about that. Or can it incorporate, different kinds of cookware? This is an important consideration because, there was an example of people developing solar cookers, for instance, in use in villages and so on. But the villagers use certain types of cookware which may not fit there, or it's not the right geometry or whatever. And if that's not considered, then it's useless, right? So something kind of not necessarily technical, but we need to be aware of it. And this is important, and the only way to know about it is by really understanding who is going to use your technology. That's why that closing the gap between you as the innovator and the person who actually who's going to use your innovation is very, very important. And hopefully we'll try to close that in this class. The sunlight collection area, are we talking about very large? You have plenty of space, or is it very space constrained? Larger collection areas, we know if you put a big collector in, you can get higher temperatures, as long as the heat loss is not increased. Proportions. So let's talk briefly about this. Is a square box better than a rectangular box? Any thoughts? We're using a very simple example because so we can think in more common sense before we go into details of the optics. But any thoughts? Yeah.
Would a rectangular box be better if you aligned it with the travel of the sun?
Yeah, exactly. Yeah, this is exactly my point. So, of course, we talked about tracking. So if you have a square box and the sun is on one side, you're going to cast shadows. But if you have a rectangular box which is a little longer along the axis of the sun, then you can minimize the shadows, so you get a longer hook. So very simple ideas like that. Right? So this is important, by the way, when we talk about solar concentrators, because that axis, as we know, tracking is critical. We'll talk about one-dimensional concentrators versus two-dimensional concentrators and things like that. And the choice of what you do will be driven by what it is being used for. If it's a very quick thing, you just need a very high temperature very quickly, then you don't care. And when you want something very long, slow, and we'll talk some examples today about very slow things, like for water desalination, things like that. So it's important. Now, which direction should the rectangular box be oriented? You answered it. Obviously, it should be in the axis of the sun, right? To minimize shadows. Tracking required? In general, no, because if you're not doing any concentration, you don't need tracking, but to avoid shadows, you might want to use tracking. Of course, tracking increases cost, weight, things like that, maintenance. So tracking is probably the most biggest challenge in, I would say, using concentration systems in solar and solar thermals today. So lots of interesting things happening in that field. The other things to consider, again, non-technical stuff, is what are the challenges to adoption? So because this has been tried for many decades, so we kind of have a list you can look at. Is the taste of the food good enough? Maybe if people don't like the taste, then it's not going to be used, right? So again, something we don't think about. So do you need precise temperature control? You need to turn it up and down, whatever. What happens if cloudy days cause disrupting traditional gender roles. So very interesting things that might happen. But nevertheless, the point here from this very, very simple example is that there are many, many opportunities for technologists, as we will talk about today. So today, my real goal is to give you a flavor for many problems that could be addressed with optics used in an innovative fashion for energy purposes. And hopefully you can utilize these topics to think about projects for the semester. Okay, so that's really the goal for today's, and it could be solar equipment, but we'll talk about a few other things today as well. That's the goal for today. Of course, new market opportunities as fuel prices increase. Also it's not just a question of technology, it's also a question of can you innovate on the other side, right? Microcredit, whatever, or the sharing economy, whatever. So that's why this latter half of this class really deals with entrepreneurship. So it's very important as technologists to really think from that end. Not necessary to innovate from there, but it's an option, something to think about. Can we incorporate solar cooking, home designs, whatever, architecture, things like that. Okay, so that was actually the rest of the lecture from Tuesday. So before I go on, are there any specific questions on assignments or classes? Exam, anything like that? Everyone okay? Good. So today's goal, I want to go basically relatively quickly through a bunch of different project ideas. Think about them as just a survey, and we'll kind of look from a big picture point of view because we haven't gone into the details. And then next week, remember I mentioned that I'm going to start assigning teams and assigning topics. So very, very important, if you want to work on a specific topic or you want to work with certain people, you need to email me, otherwise I wouldn't know. Okay? So you have until probably next Wednesday or so. After that, I'll start basically signing. Okay, so let's jump right in. One of the first ideas is solar water pasteurization. Now, of course, water is very important. We live in Utah, so we know this. But something like 1 in 6 people on this planet have no access to clean drinking water. That's an incredible number, right? It's about more than 1 billion people. Half of the hospital beds in the world are filled with people suffering from water-related diseases. 80% of deaths in children are due to contaminated water. Now, water pasteurization is different than water desalination, and we'll talk about that. But pasteurization, of course, means that you want to make it drinkable, but not necessarily 100% pure. You want to get rid of bacteria and things like that. Potentially, you can use it for cooking. Right? So let's see, and this is a very simple. There are many, many simple technologies that can do this. So let's think, let's see what they are. So what can we do about it? So we know that heating water to about 149 degrees Fahrenheit, about 65 degrees Celsius, pasteurizes water, killing disease-causing microbes. Something like 99.999%. So there's no need to boil the water. That's a very important thing to keep in mind, because there's a big difference in energy between boiling water and pasteurizing water. And here we are very stingy with energy. We don't have access to energy, let's think. Okay, so that's very important distinction. And pasteurization is, of course, used in milk. It's a use of moderate heat to kill disease microbes. Milk is pasteurized at 71 degrees, so a little higher than water, for 15 seconds. So it's relatively quick, right? So this is an example of something which can be very quick, as opposed to slow cooking. Studies show that 99.999% of bacterial water can be killed at 65 degrees Celsius in 60 seconds. So that's nice. It's a nice metric to know. Okay, so far so good. So let's take 30 seconds and you can discuss among yourselves. So this is a nice thing, relatively easy to do. What problem do you see with this? Just with this statement here, and maybe I want you to discuss with your neighbors for like a few seconds, let's say 10, 15 seconds. Because it's useful. If you don't know each other, introduce yourself. So in my class, I'll make you talk to people. And there's a reason for this. Any thoughts?
What's the temperature?
100 degrees Celsius.
Yeah, you know for sure.
That's okay.
Yeah.
I mean, there's.
Yeah, you still
Yeah,
so maybe there's other things that other minerals and stuff.
So this is
Or viruses.
Yeah, anything like
So that would be
Yeah, I thought you had to get up to boil. I didn't know.
There's so much filters today.
And
And they have filters down there.
That's not a problem.
But not all of them. So there's a difference between water purification and
That's how you can do it. How do you maintain the temperature?
Yes.
So there's probably more than this. You gotta have a couple.
Yeah.
Yeah, to get the best one, you want to filter.
Still have to make that.
Anything interesting to shout out?
It's the filter.
Well, this class will be kind of discussion.
Yeah.
So feel free to shout.
We were kind of talking about the fact that if you're doing any kind of large amount of water, you're gonna have a hard time getting it to that temperature for that long of a time.
Yeah,
also,
that's similar to what you were saying.
you also have to do this in a clean environment, because if you pasteurize the water
And then take it out into
Yeah.
something that, yes, good
not
point,
clean,
yeah.
then you have a problem again.
Anything else that they might have missed that you want to add?
We were talking about how
And there are no wrong answers here, obviously. I mean, it's like a design problem, really.
if you don't have a thermometer with you, it's hard to tell that.
Yes, that's the problem I was trying to get to. How do you know it's 65 degrees?
That and just because part of the water is at that temperature doesn't mean that all of it is. So how do you make sure
Exactly,
that all
yeah.
of your water is at that temperature for that amount of time
Yeah.
instead of just the surface water, which might be hotter, or
Yeah.
depending on how you're heating at the bottom, which might be hotter.
Yeah, absolutely. I completely agree. Yeah. So the two big problems I would say is one is how do you know it actually reads 65 because you can't see, right? Without the thermometer. Thermometers may not be available, let's say, in these places. And the other thing is how do you ensure that the whole thing is uniformly heated? So the problem that you're raising is not necessarily easy to solve, but the problem you're raising was the first that was the main reason why people could not use it. They had to boil it, right? Like if there are floods or something like New Orleans, you have to boil the water because you don't know for sure. Now, so this company, so let me put this actually. This allowed them to come up with a material that melted at 65 degrees or changed color or something, and you will see. That was a very simple innovation that enabled this whole thing. That's important because the difference in heating water to 100 degrees or 65 degrees is a big difference in terms of energy, right? Especially as you think about what. So this is an example of a very simple, interesting innovation that I think is elegant. So it's a temperature indicator at 65 degrees Celsius. So they call it a water pasteurization indicator or WAPI, and it melts essentially. It's kind of cool. So it's a short video. We can.
Pasteurization indicator is a simple device that indicates when water has been fully pasteurized. A plastic vial with the wax on the top and the washer on the bottom is placed in the middle of the pan. When water is heated to the pasteurization point, the wax melts and drains to the bottom of the vial. When cooled, the wax hardens again, and the WAPI can be turned over and reused again and again.
Okay, so that's pretty simple. So I guess partly you can solve it by moving it around, I suppose, and look at it, but it's not an easy. I suppose if you have small amounts of water, it's not a big deal. Okay? That's a good point. Maybe it's a problem you guys can try to solve. So what other technologies exist? What do people do? Okay, so of course one thing we all know is we can simply use a solar cooker, right? That's a simple panel cooker. You put your water in the focus of where you have to put it. It's an approximate parabola actually. We'll talk more about that later. But that can heat it up. Or in this case, there is another example which let me see if I can play this video. It's actually pretty quick, so.
Are exposed to biological pathogens in the water they drink. The Aquapack uses solar energy to kill these pathogens using the proven process of heat pasteurization. Simply fill the Aquapack with up to 4 liters of water, place in direct sunlight. Orange water pasteurization indicator. After a few hours, the orange color disappears, indicating the pasteurization temperature has been reached and the water is safe to drink. The Aquapack can be inexpensively manufactured in developing countries for about $2 each, providing both jobs and safe drinking water.
Okay, so that's an interesting option for sustainability, obviously. So really all you need is some sort of way to create a greenhouse effect and be able to know when the temperature is reached for pasteurization. Okay. So one of the simplest solutions that I could find online was basically there's what they call sodas, which basically they put water in a little soda bottle, PET bottle, and out in the sun for many hours. And essentially the UV rays will kill most of the bacteria in addition to the temperature. So it's kind of a twofold effect. PET allows UV to pass through. Of course, some plastics don't, so it depends on what you use. PET, by the way, is a type of plastic. I won't play this, well, maybe let's take a quick look, but so you have an idea what this means. So basically they use bottles like these. So pretty simple, right? Okay. So, skip through. So before we go on to desalination, so pasteurization is like a very simple problem. It's relatively simple solution. I mean, potentially you could think of better ways to do it. Right? That's what I mean by a problem. And then you can try to innovate somehow to improve or solve the problem. Right? You can try to identify some problems with this. So if you recall, my assignment 1 had to do with understanding the landscape, recognizing the problems, right? And that can be not just technical, it can be cost, portability, usability, whatever, right? And trying to identify that, doing that literature review, online search to recognize that. Okay? So let's move on to the next issue, water desalination, which of course, again, we are all very relatively familiar with. Very important problem, right? It's interesting, by the way, from this map, that this is the water, what they call the water stress indicator. So when it's very high, like where we are, it also coincides with where there's huge solar resources. Okay? There are only 2 countries in the world today which can do water desalination on a large scale. One is Saudi Arabia, for obvious reasons, because they have oil and no water. It requires a lot of fuel, as we will see. And the second is Israel. And the only reason Israel does it is for geopolitical reasons, because they don't have access to water from freshwater sources, because of the countries around there at war with countries around them. But most of the countries can do it, and it's not possible because it's really, really expensive. So that's a very important problem. As an example of an important problem, the solution really doesn't exist. Someone needs to innovate. Someone needs to come up with a solution. And we'll talk about solar opportunities, because that can avoid this whole requirement of fuel and hopefully reduce costs. In the US, I think there's only a couple of plants, and the biggest one is near San Diego. But it's also relatively not that heavily used. And it's expensive for obvious reasons. We'll come to that. So desalination is, of course, how we all get all our water, all fresh water, from the hydrologic cycle. So what happens, of course, is that water from the oceans evaporates by the sun, leaves salt behind, and that's basically distilled water, right? Forms the clouds and rains down, and whatever is collected gives you fresh water, or what percolates down into the ground. And of course, majority of it reaches back the ocean again in cycles, right? Like our Great Salt Lake is right there, but it goes back up straight. It doesn't reach the ocean, but it's a little bit different. So we want to somehow create an artificial version of this that is cost effective, right? And that we can control. We can turn on and off to some extent. This is really our goal. Because if we can, then that will solve this massive problem of water. Doesn't exist yet. We'll see some possible things that people are looking at. So the obvious way is to essentially filter the water, right? And filtering water is based on a principle of osmosis, which we have all learned in high school physics. In osmosis, what happens is that, let's say, we have a very salty water, shown in blue on one side, pure water, which is shown in light gray on the right-hand side. And let's imagine we have a filter in between separating them. And the filter allows water molecules to pass through, but will not allow salt molecules to pass through. So salt is ions. So salt exists as crystals, but it can be ions as well. But anyway, let's imagine that crystal. Salt, NaCl, is bigger than water. So you can have filters that allow water to go through, but not salt. Okay. Those exist. In fact, that's one of the big problems. We'll come to that. So what happens, of course, is in osmosis, is you have a concentration gradient. So if you look at this, there's a very very high concentration of water here, lower concentration of water here, right? So concentration gradients always lead to what's called diffusion. Some of you have learned either in semiconductor physics, 3200, those of you who are in ECE, or in mechanical engineering, I'm sure you've learned about, or material science, for instance, you have learned about diffusion through concentration gradients, follow some hyperbolic profiles and so on. But we won't go into the math. But the only point is that the water molecule concentration is high here, low here, so it'll start going. Always tries to match the concentrations. Right? It relates to a potential energy, but just think about this as concentration. Now, of course, when this happens, the salt cannot go through, salt is prevented, so this equalizes until both of the, this becomes more dilute, essentially. The pressure will go up. Now, you want to, of course, do the opposite. You want to take the water from here and put it here. So you're going against the laws of thermodynamics, right? Laws of thermodynamics forces diffusion of water from high concentration to low concentration, of pure water to impure water. You want to do the opposite, right? This is the second law of thermodynamics, is what's happening here. We'll see this later on. It's increasing entropy. That's basically what's happening. But we need to now decrease the entropy, which means we need to do some work. And the only way to do the work is put pressure on this water. Push it through the filter in the reverse direction. But of course, because the filter prevents the salt from going through, salt will be trapped. Only the water goes through. So you get pure water. Now you can see the problem here. There are two problems. One, of course, you need that energy to push it through. And the worse, the more pure you want this, and in other words, the difference between these two, the higher they are. In other words, if you want more pure water, you need to put more energy, right? You need to push through. That's a lot more salt. Okay, that's one problem. So you need lots of energy. The second problem is that think about the filter. All the salt is getting trapped here. So after a while, this filter will not be effective anymore. It will get clogged up. It needs to be replaced. Two massive problems in desalination. Very simple to understand, but huge problems affecting billions of people. So if we can come up with an innovation to solve these problems, you'll be a billionaire, and you will improve lives of billions. So this is the idea. Reverse osmosis, we need energy to push water through the membrane. Of course, that energy can be produced by photovoltaics, which is the most obvious way to address it, right? You have solar panels and then a pump. Okay. It's not as simple as that, so we'll see why. Okay, so of course people use photovoltaics as a primary energy source. So I'll show you a simple example, and we'll talk a little bit about why it's difficult. So we have our solar panels here. We have some control electronics. There's a tracking system if you want. There's a pump. So that's the pump which is pumping the water through the filter, right? Through our very simple schematic we saw. And then the clean water comes out. So the filters are here. They usually put them in little interleaved layers. So it's not like a simple one thing that you see. Usually there are many interleaved layers, goes through multiple filters. So you have different stages of pure water. At the end of the day, you engineer it such that you get final clean water into some kind of storage. So it's used in portable systems. It can be portable disaster relief. Now, there is a control problem here, which can anyone recognize? Maybe some of you are from mechanical engineering can think about this. Any thoughts? So the pumps work like it's a motor, right? Motors work most efficiently, like when you drive your car, where is the most efficient? When you're going on the highway, right? When you have a constant speed. You brake and speed up, it's not very efficient. Same thing, right? It's a motor. Pump is a motor too. Same thing. You want to have a constant speed, right? But if you use sunlight, you have a problem. You have clouds going by, you might have, rain or whatever, right? So you will have this variability. So that becomes an optimal control problem, which means that you need to have a battery attached to it. You need to have some sort of feedback loop which sees what's happening. If it's going to drop, then suddenly you get energy from the battery. Right? You want to keep it as efficient as possible. And it's important because you don't want to have stop and starts. So this is just a demonstration system which was built at MIT that tried to do this. So let me see if I can. There's no volume, but this is on the roof, and you can see it's tracking the sun. What this is showing is the solar radiation in watts per meter squared. Okay. Function of time. And you can see the clean water being pumped in. So there's the filters, and it's removed, and it got full, and more got pumped in. But what I'm showing you was all these jumps are clouds, and of course this is in the morning, this is during the midday, and then of course the evening goes down. So they have to have some control system which accounts for all these jumps. Okay. It's also not good for the motor to get different currents, right? It will get damaged. Okay. So what? But that's a solution that was that's a solution using electronics or some sort of controls. Right? Is there an optical solution? I don't know. I'm posing this question to you. Is there a better way, a different way to do it? Right? I'm not. You don't have to answer it. Right? I'm just posing it rhetorically. But it's a problem, interesting problem. Right? You could somehow do it optically. Not obvious how. So again, my goal here is to basically put questions in your head so you can start thinking about problems to solve for projects in the semester. Okay. Again, as I said in the last class, I'm not saying you have to pick any of these, but I'm just giving you examples that will spark ideas in your head as a team so you can think about it. Okay. Now let's look at a few other simple examples of desalination, which are completely passive. So the last few examples we talked about are active desalination systems. There's energy input actively from a pump, panel, or reverse osmosis. Here we're going to think about what are called passive systems. So this is, for instance, what's called a salinity gradient solar pond. So it's a pond. So it's a big pond of water. Okay. Let's see if we can zoom in. Actually, I think you can see. So sunlight heats up. So the high salt content, the denser part of the water, goes to the bottom. And the denser water, the saltier water, will get hot faster. Because NaCl will absorb more than H2O. But because it's together, it will come back to heat. So that layer will get hot. Okay, sink to the bottom. And then you have a small gradient layer, which is medium heat. It basically acts like an insulator between the bottom and the top layer. And then you have a top layer which remains relatively cool. And that's interesting because that's the part that's seeing the light first. But it's transparent, it's water. Right? So only very little part of the water light is absorbed. All the visible light is transmitted, most of the UV is transmitted. Some of the IR is infrared is absorbed. But salt water can absorb the visible, for instance. Especially if you can see through it. That gives an indication. So this temperature difference, we will see this again and again, is essentially an opportunity to do work. Temperature differences, two bodies with two different temperatures is almost always what you need for anything to do work. And we will call this a heat engine. Again, you'll see this again and again, many examples. Okay, so it's a very, very simple example here. So what happens here? We have the hot water piped through here, okay, into a chamber where there is an organic working fluid which evaporates. So it's a fluid there, liquid there, generally an organic liquid, because it's in contact. So it's in contact with this hot pipe, it will evaporate. Okay? As it evaporates, it is going to extract, well, it can do work, for instance, not important, but it can extract heat from the surroundings and cool the surroundings. That's how, for instance, we'll do refrigeration. We'll come to that soon. But let's ignore that for the time. It's going to evaporate, and it'll go through this pump. Okay, so now it's a gas. So you see, it's not a pump, sorry, a turbine. This gas will go and run a turbine. Right? Run a turbine, create electricity, low-level electricity. So it's a generator. Very simple, right? There's no dam or anything like that. It's just very simple. But very low levels of electricity, it's not huge amounts. Then, once it has done the work, it's going to go here and condense on the cold side. So the gas comes in, you see a cold environment, cold surface, it will condense, form liquid again. Now, of course, when it forms liquid again, it is releasing heat, right? Because the gas has more energy. So this part will get hot. So we'll talk about that later. But this is a cold, that surface is maintained cold by the top surface of the water, which has been piped in. So this is what I mean by the cold part and the hot part, and we're getting work being done in between. In this case, electricity is being generated, low levels of electricity. So just to review, so the denser salt clear water heats up at the bottom, the middle layer acts as an insulator, top layer remains cool, and it produces low grade, less than 100 degrees Celsius thermal energy. So it can be used for heating, right? You can pipe it into rooms or whatever. It can also be some electricity production. Generally, the efficiencies are 10 to 15%, so not great. One nice thing is that this can still work even if the days are cloudy. And we'll talk more about diffuse and direct sunlight, what I refer to here. Direct refers to the situation when there are no clouds. The sun rays are coming straight. Diffuse refers to the situation where the rays are very diffuse. And this, for instance, is diffuse light. And one good way to tell is it does. So it's actually not that diffuse. By looking at the shadow, you can tell if something is diffuse or not. If it forms a very sharp shadow, it's not diffuse, direct. Like a laser. It forms a very fuzzy shadow like this, diffuse. This distinction will become very important when we start talking about solar concentrators. Because solar concentrators, because of thermodynamics, will not work well under diffuse sunlight. There's a fundamental theorem we'll talk about what those trade-offs are. Okay? So, which is another reason why we need tracking. Also comes to that. Everything is kind of connected, which is interesting. Okay. You can, of course, do a more active heating, like the solar cooker. In this case, a parabolic trough collector. So basically, you have big, long tubes which contain some fluid. Okay, it can be water, but it can also be some other fluid. If you use some other fluid, you would run a turbine. So if it's water, you can use for desalination, right? Distill the water, basically. So you have you put these tubes in the focus of the parabola. So that's the parabola. Now it's a one-dimensional parabola, right? And one-dimensional because you don't want to have to track the sun as it moves. So this 1D parabola is a degenerate in the opposite direction, which means that it doesn't matter where the sun is, it'll always still focus a line. Okay, we'll come to this again when we talk about solar concentrators. So that's why they do it this way. And they have many panels, and that's basically for transportation and ease. It's a modular system. So if the sun comes in, it heats up the liquid. If it's water, it distills, then you pipe it out. Of course, in that case, you have to be careful because whatever is not evaporated remains in the pipe, right? So that means it needs to be cleaned periodically, or it can corrode the system. So again, another thing to think about when we design these things. Maybe there are better ways to do it. So generally speaking, people use these for electricity. So heater transfer fluids can be used for high-grade thermal energy or electricity production, or thermal distillation, which is what we are interested in here because we're talking about desalination. Of course, some tracking is required, right? Why? Because this axis of the sun is not constant every day, right? It's slowly changing. We know during the winter the sun is over there versus over there. So this axis is changing. So we'll talk more about that. So some tracking, of course, is needed. That's relatively slow and simple, manually. Right? It doesn't need to be expensive, but it can be. Of course, you can also do the 2D version of this, but then the mechanics becomes more complicated. How do you bring the water and bring it out and things like that without shadowing the systems? Okay. Another simple system which, for instance, can be combined with greenhouses used to grow plants and things like that is what's called a single effect solar still. It's called a still. It's basically like a pond. We'll talk more about the greenhouse in the next slide, but it looks like that, very simple. Okay, so basically a piece of glass, or it can be plastic, but generally glass. There might be a reflector here. Dirty water is pumped in, okay, and it just sits here like a pond. Heats up from the greenhouse effect. The whole thing is enclosed, right? It evaporates. It condensates on the top glass layer. You try to keep that cold. Hopefully that glass doesn't absorb a lot of heat. And it will simply flow down here. It's collected in this trough, and the water can drain out. Simple, right? Very, very simple. And you can imagine doing some clever optical designs here to make it better, right? I think you can already probably start thinking of from very common sense without even knowing any optics. Now, so this is simple, inexpensive, but slow and useful for small amounts of water. So let's do a very simple example just to get, in this class, by the way, we will, I need to bring markers. Okay, it's okay. In this class, we are very interested in understanding back of the envelope calculations, rules of thumb. So let's do one very simple example, and you can discuss among yourself. Let's say the energy, I'm telling you, the energy to evaporate 1 kilogram of water. So let's say your water is a kilogram at 30 degrees Celsius. So of course, the energy depends. So to evaporate, you want to boil it, right? You want to get to 100 degrees. But that's only true at atmospheric pressure. So you need to know what that pressure is. So I'm not giving you all the information. I'm just giving you the total energy. So it's not so important we need to know all this detail. I'm just giving you the energy. Let's imagine we start at 30 degrees. I'm going to evaporate a kilogram of water into steam, water vapor. It requires 2.4 times 10 raised to 6. Sorry, that 6 needs to be up here. So 2.4 million joules of energy. Okay? I want you to, and then I'm also, so that's what you need. I'm also going to tell you the solar insolation, which is the intensity of light from the sun, is 250 watts per meter squared. We'll see that number is kind of low here. It's much higher if it's a beautiful sunny day, but let's use this for now. Watts per meter squared, so it's Bay Area. How much water can be produced per unit area per unit time, assuming that's 100% efficient, let's say. All that energy is being used to produce water. It's very simple, but I want you to think just, you can write it down or talk to your neighbors, whatever. It's really important to understand the units and kind of get a sense for feeling for it more. So just try it yourself. You can discuss if you want. And you can do it in your head if you want, it's fine. And these sorts of problems, I want you to be able to get a sense of how to address them. So I might ask you in the midterm, right? This is, of course, very simple. So probably won't ask you something this simple. But let's take about 30 seconds.
So that's just 2.4 times
10 raised to 6 million. And that's 6
10
there.
to the 6.
Yeah, that's my typo. But it's okay. I don't care particularly about the numbers. Just tell me how you would address it. The problem. That's much more important. So anyone want to? I don't care about the answer. Don't shout out the answer. Tell me how you would. That's all I care. Yes. So exactly. So we'll first think about that's joules, that's energy. Watts per meter squared is what's coming in, which is watts is what? Is the power, which is joules per second, right? So that's how much energy is coming every second, every meter squared, right? So all I need to do is take that and what do I do? Actually take that and divide it by the unit rate. Right? We need the total divided by the rate. And that will get the amount. So in other words, that's joules divided by joules per second per meter squared. What will I get? Meters squared per second. The joules will cancel out. Okay, does everyone see that? So what you'll end up with is every second, so I made a mistake. So that's joules per kilogram. We shouldn't forget that. We shouldn't forget the kilogram because that's the answer we're looking for. So you take this joules per kilogram, you divide that by joules per second per meter squared. The joules cancels out. Okay, what you get is second goes to the top per meter squared per kilogram. Then you need to invert that. Okay, I should probably still have a marker.
If you want, I've got a marker.
But instead of the exact numbers, I want you to know how to think about the problem. Right? This is the amount of energy coming in. Thanks. Thank you.
Sure.
Whoops. I lost something.
It's right here.
Is this yours?
I got no throw.
I don't know if that's yours or not. Oh, that's the battery, never mind. Put this down. I guess deal with that later. So what you have here is we have 2.4 times 10 to the 6 joules per kilogram. So 1 kilogram of water requires that many joules. What's coming in is 250 joules per second per meter squared. So the question is, how much water can be produced per unit area per unit time? So the answer will be something like kilograms per meter squared per second. Right? How much water per unit area per unit time? So if you take this divided by that, right? You'll get that if you take that joules per second per meter squared, divide that by joules per kilogram. This is all. This will be kilograms. Let's see. Both in the denominator per second. Right? This is what. Is that okay? Very conceptual. Right? And then you can plug in the numbers. Well, it's simple. It's just the rate, how much you need to do, right? What you're getting, divided by how much you need per unit. Then you get kilograms. Now, if you actually run the number is really, really, really small. Right? A million goes in the denominator.
100 micrograms.
I don't remember the number, but you can work it out. Maybe, it's about 100 there, 10 raised to 4, so 10 raised to minus 4 kilograms, so 0.1 milligrams, yeah, so about 100 micrograms. So it's very small, that's the point, right? That means that, you need quite a lot of energy, or you need a lot of time, or a lot of area. So we need to, I had two goals in doing this exercise. One is for you to gain some intuition on looking at units and kind of understanding what to do with them. And the other thing is to get a sense for scale of what these things are, right? Is it big, small, things like that. Okay. Of course, that's assuming 100% efficiency. In reality, that's 30 to 40%, so you have to scale everything accordingly. So where is that? Yeah, about a half of that, less than half. Material selection here is of course very important, and you can think of huge numbers of system improvements here, even with optics, concentrators, whatnot, right? Fiber optics, whatever, right? So something to think about. You can combine these with greenhouses. So this is fairly popular in some greenhouses. So let me just zoom in. This is kind of an interesting design, just so we can appreciate it. Similar sort of situation. You can grow plants, whatever. Inlet, water is here. Sun comes in, evaporates, heated by the sun, and condenses on the top surface, comes in, collected by this distal water gutter, and then the water is taken out. So it's sloped here, so the water will flow out, and there's extra water gets out. You can also engineer things like heat absorbing surface at the bottom, things like that. Pretty similar. Okay. Oops. Okay. So saline water is pumped to the south-facing roof, and in this case, the south-facing, the top cover still is glass, but bottom passes wavelength suitable for photosynthesis. So in this case, we have to be aware of what it is that we're doing. Okay, you want to make sure all the wavelengths of photosynthesis pass through. 380 to 710 typically. Temperature of the greenhouse is lower, which is nice, so the plants don't get too hot. Water vapor condenses on top of the stones collected. It's used for greenhouse agriculture. There's very little access to fresh water. Of course, one of the big challenges is corrosion of the collector due to contact with saline water. So this stuff will corrode fast, so you don't have to deal with that. Again, you can start thinking about approaches in optics to improve this kind of thing. So just to summarize, we talked about two different kinds of desalination. One, I would call it active or direct, where you use solar directly to create the distillery, right? Tough concentrators and whatnot. Or the other option is small scale stills and so on. We just talked about where you just passively allowing the water to evaporate. Or indirect, where you use the solar to produce energy, the photovoltaics, and the energy is used in a separate system for display, so you run the pump. It can also be solar thermal or photovoltaics. We didn't talk too much about it, but you can also have solar humidification, dehumidification systems. All of these are very similar in the sense that once you create a hot end and a cold end, you can actually do work. Okay. In this case, the work was creating electricity. We saw that turbine. The next example, we'll see that it can be used to refrigerate. It can also be used for humidification, whatnot. Right? Everything. Once you have a hot end and a cold end, it becomes a heat engine, and you can use it to do work. So the next topic I want to talk about, and it's probably the last topic, is solar refrigeration. So the question, this is a very, very interesting question, an important question, because is it possible because this is a big problem in the majority of the world. Can you use sunlight to keep foods, medicines cold? Can you make ice? Right? Of course, disaster relief, incredibly. So before we talk about this, we need to understand some very basic principles of vapor compression cooling. In other words, how does this hot and cold ends, how can we use this hot and cold ends to actually create cooling? And that's general. It has nothing to do with solar or anything like that. It just comes from thermodynamics. So let's look at understanding that simplest possible heat engine from the most common appliance that we all use, which is the refrigerator at home, right? So there's a very simple video, which is only about 2 minutes. So let's take a quick look at it. And I'm gonna disconnect that. And it's useful for us, although it's simple, to understand
Picture of what's going on in the refrigerator, and I'm basically showing you some tubing, metal tubing, aluminum tubing, some kind of metal tubing, and a couple of devices, a compressor and an expansion valve. Let's just see how this thing works. So the working fluid is sometimes a gas, and I've designated that by red, and sometimes a liquid, and I've designated that by blue. So what happens? Well, there's a compressor. The compressor is a pump that pressurizes the working fluid and pumps it around in this loop. And so when the compressor gets a hold of the working fluid, it compresses it, and it becomes a high-pressure gas. And then that fluid moves through some coils, sometimes in the bottom of the refrigerator, which is actually a rather poor place for it energy efficiency-wise. Better places on top, and you might have seen ancient refrigerators that actually have a little round thing on top, and that was a better place to put these coils. Sometimes in the back, sometimes they're in the bottom. But the purpose of those coils is to take that high-pressure gas and let it get rid of some of its energy,
in the process condensing to a liquid. So as it goes through those coils, it gets rid of some of its energy. It rejects that energy to the outside environment, the room the refrigerator is in. Translation, if you touch the coils of the refrigerator, either underneath or in back, they're warm. They're giving heat out to the room that the refrigerator is in. A refrigerator, ironically, gives off heat. Well, not so ironically. We'll see why in a minute. Okay, so now we have the working fluid in liquid form, but it's still at high pressure. It's rejected this heat to the surrounding environment. Then it moves through the expansion valve, and the high pressure liquid going through this valve, which is basically just a tiny hole, in a tiny little orifice where the gas is forced to go through, and as it goes through, it expands, and cools, and becomes a low pressure liquid. So now we have low pressure liquid, and the low pressure liquid is then circulated through a series of coils that are insulated from the outside environment, but they're in contact with the innards of the refrigerator. And heat flows, again, that's the right term because heat is energy flowing because of a temperature difference. Heat flows into these cool coils, and it evaporates the liquid, and it takes energy to evaporate the liquid, and that energy is ultimately extracted from the materials inside the refrigerator. It goes into the working.
Read by internet, but good.
And the cycle starts over again. The net effect of the refrigerator is simply to pump heat from inside the refrigerator, from the contents, to the outside.
Okay, so basically, what has happened is that this is the cold end, this is the hot end, right? What the cold end does is it extracts the heat from inside the refrigerator, and the hot end, of course, disperses it in the environment. The result, of course, is that this region becomes cold. So our goal, and in a traditional refrigerator, what happens is that this compressor is run by electricity, right? So what our goal is to create this hot and cold end without hopefully relying on fossil fuels, right? Either using PV, photovoltaics would run that, or some other ways. But that's what we're going to think about. So let's. So let's look at two different options. The first one is with PV. That's a straightforward one. So solar electric refrigeration. So pretty straightforward. We use photovoltaic panel, the energy from the sun. So that's the work coming in to the system, QS, which is the insolation or the intensity or the watts per meter squared multiplied by the area of the panel. Okay, that then gets converted into electricity, which runs the motor. There's some efficiency there. And efficiency loss there, which runs the compressor, which runs that cycle we just saw before. Okay, so we have evaporator here, and then it gets that fluid gets that is a gas that gets compressed, becomes liquid, condenses. So that's the cycle. This is the heat being extracted from inside the refrigerator. Excuse me, and heat here being dispersed into the environment. Okay. Same exact cycle we just saw, and in fact, any energy work, any system that does work can be modeled this way. Almost entirely. There's some exceptions in quantum mechanics. So, first, one of the big challenges is grid connection, whether your battery. Like we talked about before, motors should be run typically at a constant speed. So how do you deal with variable capacity compressors and things like that? Overall efficiency is 20-30%, but they're relatively expensive. Why? Because it needs a lot of energy, right? So you need big solar panels, or you need a long time. Not a great solution. It exists. Better than nothing, right? But maybe there are interesting ways to improve that. The second example is a thermoelectric system, which of course is not mechanical, so it doesn't use a conventional fluid. It uses an effect called the Peltier effect. So it's also called a Peltier device, named after the person who discovered this. It couples heat and electricity. Okay, so basically you have a PN junction, which basically all it means is it's a transistor. It's part of the transistor. It's basically one side is highly enriched with electrons, and another side is highly deficient of electrons. And it creates this gradient of electrons between them. Not so important for us to understand that physics at the moment. The only thing that you need to know is that instead of running a compressor, here you can get cooling by simply connecting a battery. And it's what's called a solid state cooling. So there's nothing moving around other than the electrons themselves. So it's very, very robust. And this is very commonly used, for instance, in space, like the Mars rover uses things like that. They're very expensive. It's very lightweight and very reliable. So how does it work? You connect a battery. Electrons flow out of the negative terminal of the battery, comes this way. It flows from this side to this side. Okay, that's the electron flow. The electrons take the heat from one end, from this side, and takes it to the other end and releases the heat. Here, the opposite happens, but it's still, from a thermal perspective, it's the same thing, but the heat is now conducted by the holes. Holes are basically an absence of electrons, so it's a little strange, but bear with me. So the holes essentially come out the positive terminal of the battery, goes through here, travels in that direction, it's the direction of hole flow, and absorbs the heat from one side and rejects it on the other side. The net effect of this flow, and of course these electrons and holes will essentially combine and annihilate each other. Okay, they undergo what's called a recombination reaction. Not so important from our perspective. The net effect for us is simply connecting this battery. One side gets cold, so this part is absorbed the heat, right? Gets cold. This part gets hot. So we put this inside some container, it becomes a refrigerator. Okay, so no moving parts, very small, very portable, but relatively low efficiency and quite expensive, because the problem is this only works for certain materials like bismuth telluride and things like that, which are not very common, they're expensive. Okay, so in general, one thing I forgot to mention, there are a few other things to keep in mind. There are some things called Stirling cooling. There are variations of these things we won't talk about. Thermoacoustic cooling, magnetic cooling, and so on. So if anyone's very interested in this topic and you want to do a project on it, I will highly encourage you to kind of dig into it. We don't really have the time to go into all that. And some of it's, of course, outside my area of expertise as well. So, but again, the hope in this class is that you will become experts, right? You're going to have to learn new things yourself. A lot of the things that we'll do will be very multidisciplinary. Okay, so of course you can also think of solar thermal refrigeration. Again, we only need a hot end and a cold end, so we can create a hot end easily. Just use that sunlight. So you can use solar heat rather than electricity. So simple examples are shown here. So just a regular hot solar thermal heating system. Cold water comes in here, pipes through here, and there's an absorber plate that conducts the heat to the water. And hot water comes out. So you have again the hot and cold ends, and you can use those two ends to essentially induce refrigeration by running a cycle between them. The cycle is not shown; it's just the heating part shown. And of course, there are different architectures. In this case, you have a glass cover on top, and the fluid channels are basically tubes sitting on top of the absorber plate with insulation, or it can be tubes which are insulated from each other, which already contain absorber plates and things like that. Again, in these situations, you can think about many innovations you can come up with to improve the performance as well in the market. In all of these, heat is the input to engine for cooling. The challenge is, of course, the larger the collector, the more the heating, the more energy you can get. But of course, larger the collector, the temperature starts. Of course, your radiative losses go down, like we talked about last time. Right? You need to be very careful about that. Loses more heat. Also, the other thing to keep in mind is that when you have larger collectors, the absorber itself will go to a higher temperature. Right? The temperature of your hot end will get higher. Generally speaking, we'll talk about it next week. The temperature difference between the hot end and the cold end determines the efficiency of the system. The farther apart they are, the more efficient they are. Closer they are, less efficient they are. Which is, of course, common sense to some extent. But the more you make this hot, it'll start radiating more too. That's, again, comes from, I think it's the third law of thermodynamics. We'll talk about that. Okay? That's a problem, right? I start heating it, but I'm also going to lose more energy. So I have to be very careful with the design. But like I said before, the engine itself works better when you have larger temperature differences. There's this mutually exclusive things, contradictory things that are required here, which means it's a design problem. You have to optimize around that, which makes it interesting. Okay, so we're going to stop.